You've probably already lived through this. Not really, but close enough that your brain thinks it knows what it would feel like. A total solar eclipse. The sky dimming, the temperature dropping a few degrees, birds going quiet for a minute or two. People watched it happen in 2017, in 2024, and walked away thinking they understood what it means for the sun to disappear. Here's the problem with that. An eclipse lasts, at most, about 7.5 minutes of total darkness, and only across a narrow strip of the planet. What we're talking about here is different by an order of magnitude that most people never stop to calculate. 1 full hour. Every daylight point on Earth plunged into total darkness, all at once. Not a shadow passing through, a switch flipped. And the gap between those two scenarios is so large that almost nothing we observed during an eclipse actually predicts what would happen here. Start with the thing every leaf on the planet is doing right now without you noticing. Photosynthesis runs in 2 connected stages. The first stage needs light directly, no exceptions, no buffer. Photons hit chlorophyll, electrons get knocked loose, and that energy gets funneled into making ATP and NADPH, the fuel that powers the second stage, the one that actually builds sugar. Cut the light, and the first stage stops within seconds, not minutes, seconds. The second stage can limp along for a short while on whatever fuel is already stored in the chloroplast, but that reserve is small, built for cloud cover and brief shadows, not total blackout. Stomata, the tiny pores on a leaf's surface, start closing almost immediately in darkness too, a reflex meant to conserve water overnight. A plant experiencing this hour wouldn't know it's an emergency. It would just do what it does every single sunset, except the sunset would be arriving in the middle of the afternoon, with 0 warning, and ending with the same abruptness it began. That part recovers fine. An hour of lost photosynthesis barely registers against a plant's daily budget. But plants were never the system worth worrying about here. The system worth worrying about is underneath the water, somewhere most people never think to look. Phytoplankton cover roughly 70% of Earth's surface, floating in oceans that produce something close to half of the planet's oxygen. They run the exact same light-dependent reaction land plants do, but at a scale that dwarfs every forest combined, and they sit at the base of nearly every marine web food that exists. An hour of total darkness hits every one of them simultaneously worldwide, with no regional buffer the way an eclipse provides. The photosynthetic shutdown is instant and total. On its own, this still wouldn't be catastrophic. Phytoplankton deal with night every day of their existence. The real story isn't the plankton themselves, it's what happens one rung up, where animals built their entire sensory architecture around the assumption that light arrives on a predictable, slow schedule. In Tennessee during the 2017 eclipse, researchers monitoring cicadas recorded something specific. As totality approached, the insects began their evening chorus, the exact call usually reserved for dusk, and they started it in the middle of the day. Bees returned to their hives early, behaving as though the workday had ended. Birds at several monitored sites went almost completely silent during peak darkness, then resumed singing within minutes once light returned, as if wanting a kind of internal reset. All of that happened during 7 minutes. Stretch that same trigger to 60, and you're no longer looking at confusion. You're looking at a full activation of nocturnal behavior across the entire light-exposed hemisphere at once. Nocturnal predators don't wait for confirmation that night has truly arrived. Owls, for instance, rely on darkness-triggered hormonal shifts that prepare their visual system for low-light hunting, a process that typically ramps up gradually across dusk. An abrupt hour of total darkness wouldn't give that system time to fully calibrate, but it would be enough to pull many nocturnal species into active hunting behavior mid-afternoon, while diurnal prey animals, the ones whose own alertness systems are tuned for daylight, would be operating at reduced visual capacity precisely when something is more likely to be hunting them. For 1 hour, the predator-prey balance that's been tuned by millions of years of evolution would be running on the wrong clock in both directions at once.
Then there's the part of this that happens inside you, specifically, regardless of where on the planet you're standing when it starts. Melatonin release in humans is triggered primarily by light levels hitting receptors in the retina, not by an internal clock alone. Drop the light to near zero, and the body begins ramping up melatonin production within roughly 20 to 30 minutes, the same mechanism that makes you drowsy at dusk. An hour of sudden darkness would be enough time for that hormonal shift to genuinely begin. Not fully, but enough that millions of people would report a real physical wave of sleepiness arriving in the middle of their afternoon, followed by a disorienting jolt of alertness the moment light snapped back on, and the body realized the signal it had just acted on no longer matched reality. That's the biological side. The infrastructure side might actually be worse, and it would happen faster than the biology does. Solar power generates a meaningful share of electricity across parts of the United States, and in some regions during peak daylight hours, solar accounts for a significant fraction of the grid's active load at any given moment. Total darkness, arriving instantly, would functionally act like every solar installation in the exposed hemisphere going offline within the same few seconds, the same way they do every evening at sunset, except condensed from a gradual hour-long taper into something closer to an immediate cliff. Grid operators manage the normal sunset transition with hours of lead time, ramping up other generation sources gradually to compensate. An instantaneous loss of that scale, with no warning and no ramp period, is closer to the kind of sudden generation loss that triggers cascading frequency drops, the same category of failure investigated after large regional blackouts. Backup systems exist for exactly this kind of shock. Whether they'd absorb it cleanly in 60 unscheduled minutes worldwide simultaneously across every grid on the exposed side of the planet is the kind of stress test that has never actually been run, because nothing has ever forced it to happen. Air travel adds another layer most people don't think about until it's pointed out. Aircraft rely heavily on visual reference during takeoff and landing phases, particularly at smaller airports without full instrument approach capability. A sudden, total loss of daylight, arriving with no forecast and no transition period, would force air traffic systems into emergency low-visibility procedures across an enormous portion of global airspace at once, not because of fog or storm, but because of light itself disappearing on a schedule no weather model would have predicted. So picture the hour itself, all of it happening in parallel, not in sequence. Phytoplankton across half the planet's oceans pause mid-process. Cicadas everywhere begin their dusk chorus in the middle of the workday. Owls shift toward hunting readiness while songbirds go quiet. Melatonin starts rising in nearly every human body simultaneously, a global, synchronized drowsiness with no precedent in recorded history. Grid operators on every continent scramble to replace a sudden, total loss of solar generation within seconds rather than hours. Pilots and air traffic controllers across multiple time zones manage a visibility emergency that has nothing to do with weather. None of these systems were built with this scenario in mind, because the sun going dark for an hour and then simply turning back on isn't something evolution, infrastructure design, or hormonal regulation ever needed to plan for. The systems that exist all assume light changes slowly, predictably, on a schedule the entire biosphere had billions of years to negotiate with. And then, 60 minutes later, the light returns exactly the way it left, instantly, with no dawn, no gradual climb in brightness. Birds resume singing within minutes, the same way they did during the eclipse, as though resetting a switch. Drowsy humans get hit with a confusing burst of alertness their bodies weren't prepared to deliver. Grid frequencies stabilize again as solar panels come back online together, all at once, the mirror image of the shutdown. Within a day or two, most of the biological systems would likely settle back to normal. The infrastructure recovery, depending on how badly the cascading failures spread during that single hour, might take considerably longer. What this thought experiment actually exposes isn't that an hour of darkness would end the world. It wouldn't. What it exposes is how little slack exists in the systems we've built our lives, our food chains, and our biology around. We talk about the sun as something stable, something that simply is, a fixed background condition nobody questions, but almost nothing alive on this planet, and almost nothing we've engineered, was ever designed to handle that background condition changing abruptly, even briefly, even for something as short as 60 minutes. The sun has never gone dark for an hour and switched back on. It probably never will. But the fact that we can map out in this much detail exactly how badly that single hour would ripple through plankton, pollinators, power grids, and the inside of your own bloodstream says something uncomfortable about how thin the margin really is. We built an entire civilization on the assumption that the lights simply don't go out. We just never asked what happens in the 60 minutes it would take to find out we were wrong.